All right, so on Friday we went over the rest of the history of the atom material, okay? And then I had you working on these atomic theory questions to just review that material, put it in your own words, okay, process it yourself, that kind of thing. So we'll just quickly review these and then we'll move on to naming compounds, okay? So the idea of the atom was first proposed by Democritus, okay, the Greek philosopher who thought everything was made of tiny indivisible particles, and he was right. Okay, but his idea was rejected at the time because they had a system in place that explained how matter was structured and behaved, and it made more sense, and it was come up with by people who were more respected than he was, like Plato and people like that. So it was rejected at that time because the system he had in place made more sense. That whole thing about lava being part fire, part earth, parts water, okay, it all made sense, okay, because it flowed like water and it was on fire and it came out of the earth. It made sense, okay? Tiny indivisible particles didn't, right? People just didn't buy it. All right, questions on number 1. Okay, question number 2. Well, we just talked about this. What did the Greeks believe all matter was made of? 4 elements: earth, air, fire, and water. Okay, made sense at the time because it was something that they could see, they could understand. It made sense. It was explained to them. Okay, Democritus didn't do a very good job of explaining tiny indivisible particles. He just said, "Hey, they're really small. You can't see them." Isn't that convenient? Okay, this was much better. It just made more sense. People tend to believe things that make sense. Okay, I mean, we live in a world of fake news, right? As long as it makes sense, people are like, "Oh, really? The moon's going to crash into the earth tomorrow? Well, gravity's there. That totally makes sense." No, it's not. Okay, in fact, the moon's getting further away all the time. So, yeah, just things like that. Okay, it just made more sense. So that's why they believed it, and why it was a logical conclusion. All right, number 3. During the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. They were the alchemists. Okay, the alchemists were trying to make like the elixir of life, something you could drink and be immortal. Okay, or they were trying to turn cheap substances into gold, right? To transmute one thing into another, right? Obviously, we know now that that's not possible, but that's what they were trying to do. Okay, number 4. In the late 1700s, okay, a man used the data from many experiments on matter to develop an idea on its structure. Who was he, and what were the points of his theory? Okay, who was it? Dalton. Okay. This theory has 4 points. First point?
All elements are composed of small indivisible particles.
Right. Okay, basically everything's made of atoms is point number 1. Okay, tiny indivisible particles called atoms. All right, point number 2.
All atoms of a singular element are identical, but different elements are not.
Awesome. Okay, so all atoms of the same element are identical, which we know is somewhat true. We talked a little bit about isotopes there on Friday, but for all intents and purposes, that is true. They all have the same number of protons and electrons. That all the atoms of different elements are different. Okay, point number 3.
Atoms of different
Great.
elements.
Got one here. Got one here.
Atoms of different elements can be combined in simple whole number ratios to form compounds.
Right. Atoms can combine in simple whole number ratios. The whole numbers part is important, okay, to form compounds. We have whole atoms going together, okay, to make compounds. And point number 4. Shoot.
Chemical reactions are only when atoms are rearranged.
Right. Okay. So the point number 4 is the one that says you can't turn one element into another element. It tells you here's what happens in a chemical reaction. Atoms are never changed. Okay? And it says that by saying they can be joined, they can be separated from each other, or they can be rearranged, but they cannot be changed in a chemical reaction. Can an atom be changed by other means? Yes, it can, but not in a chemical reaction. That's the point of point number 4. All right? Okay, looking at this theory now, what things do we know of that can prove some of his ideas wrong? Well, we know about isotopes. Okay, so we know that not all atoms of the same element are identical. 99% of them are, okay, but there are a few that might have a different number of neutrons and thus not be completely identical. But for all intents and purposes, still the same. Okay, and the second thing that we know now is that atoms are divisible. Not all of them, but some of them are. Okay? Really large unstable atoms can be split by nuclear fission. Right? We also know that atoms can be combined to form larger atoms in a process called nuclear fusion. So we do know that you can actually alter the atom, right? It's not a process that happens in a chemical change, but it can happen in a nuclear or physical change. Okay, so that could be like in the sun, where gravity is so strong that atoms are actually forced together, okay, in nuclear fusion, or in a nuclear power plant or nuclear bomb, where large atoms are pelted with smaller particles, and that causes them to break. And when they break, they form new atoms that are smaller, and energy is released. Okay, so those are the things that we know, right, that are somewhat not true within the atomic theory. Okay, describe in your own words the models of the atom discussed here. Give a brief explanation as to why each had been rejected or changed over the years. All right, so we'll start out with Dalton's idea. He said everything was a solid sphere, okay, which was fine at the time because nobody knew about protons, neutrons, or electrons. Okay, that persisted until J.J. Thomson discovered electrons. The solid sphere model did not explain where small charged particles were coming from. Okay, so it had to be rejected in favor of Thomson's plum pudding model, which was basically still a solid sphere with electrical charges, negative charges embedded on the surface. Okay, his idea didn't last very long because shortly after that, we discovered protons, and then we discovered neutrons, and then there was all these arguments over different models. Okay, but basically they all said that there were these three particles. Then Rutherford came along, and Rutherford proved the existence of the nucleus, right? The protons and neutrons reside in this central, small, dense nucleus. Okay, not as small as he had predicted, but still small, and that's where the bulk of the material is. Okay, his gold foil experiment was what proved that deflected those alpha particles that were shot at the gold foil. Okay, and so that changed what our model of the atom was thought to look like. And then Bohr came along and talked about where the electrons were, which is still somewhat acceptable, but we know that de Broglie's electron cloud model does a better job of explaining the movement of electrons due to energy changes, which is why we currently accept the de Broglie electron cloud quantum model as our model of the atom. Okay. Everybody all right with that? Okay, so as long as you had something in there about the process, okay, we accepted this model until this happened, and then we had to go with this model, and then this happened. Okay, it's all about the process. Okay, question number 7. As our knowledge increased, we discovered the atom had smaller parts. Name these parts, describe them, and tell where they are located according to what we believe to be true now. Okay, this question is important because I'm going to ask you to do this on your unit exam and probably on a quiz or two along the way. I'm going to ask you to draw me a picture of an atom, and I'll specify which atom. Let's just say for today, it's lithium. Okay, we're going to pick lithium because it's small and I can draw it quickly. All right, so lithium has how many protons? Nope. 3. Okay, lithium's atomic number is 3. That atomic number tells you the number of protons in the nucleus. Okay, so what I would ask you to do is draw a picture of an atom of lithium. So what I would be looking for would be a nucleus that has 3 protons. And I'm just going to put pluses inside there. How many neutrons does lithium have? 4. How do we figure that out?
The atomic mass.
We use the atomic mass minus the protons, right? So we take the atomic mass, which is 6.94 for lithium, and we subtract. We don't put a line underneath that first. We subtract the atomic number, which is 3. Okay, that leaves us with 3.94. Can you have 0.94 neutrons? No. Okay, this kind of a decimal here is the result of the different isotopes. Okay, an atomic mass is actually an average of all the atomic masses of all the isotopes that there are of a certain element. Okay, most lithium atoms have 4 neutrons, but there are a couple that have less. Okay, a couple of isotopes that have less. So when we see 3.94, we say it has 4. Okay, so it has 4 neutrons. So I just draw 4 neutrons. How many electrons does it have? 3, because the number of electrons and protons in an atom has to be identical, because an atom is electrically neutral. right? If it's an ion, if it's charged, then it's lost an electron or gained an electron. Okay, so where I would put the electrons would be, I would draw this and say they're in the cloud. And now I've drawn a picture of a lithium atom that reflects several things. This would be a 5-mark question. Okay, first mark would be for having the right number of protons. The right number of neutrons is your second mark. The right number of electrons is your third mark. Okay, the right model is your fourth mark, and having everything in the right place is your fifth mark. That means having the neutrons and protons in the nucleus and the electrons in the cloud. Okay, everybody follow me there? Pretty easy 5-mark question. I guarantee you that will be on your unit exam. I'm not saying that to trick you. It will be. Okay? You might want to write that down if you have it. I'm telling you one of your unit exam questions right now. All right, question number 8. If I have the same amount of lead, and let's, instead of saying 1 cubic centimeter, let's say I have 100 atoms, because that's more accurate. 100 atoms of lead is heavier, or are heavier, than 100 atoms of carbon. Why? Yeah, exactly. Okay, lead atoms are bigger. Okay, if you look on the periodic table here, okay, carbon only has 6 protons, it only has 6 neutrons and 6 electrons. Lead, on the other hand, okay. Oh man, why am I lost right here? Sorry, it's 82. 82 protons, and it has a lot more neutrons, okay, and 82 electrons. So it's bigger. Okay, there's just more matter in an atom of lead than there is in an atom of carbon. Okay, remember, this is kind of like Dalton's second point of his atomic theory. All carbon atoms are identical, but carbon atoms and lead atoms are different. Okay, that's why. Okay, questions on that one? All right, nuclear reactors use atoms with very large nuclei like uranium, which has 237 particles in its nucleus for fission, that is splitting of the atom. Why wouldn't they use smaller, less dangerous atoms like lithium, which has only 7?
They won't be able to carry out the fusion reactions because of
Because what, sir?
they won't be able to carry out the fusion reactions because it's not.
Yeah, there's not a lot of energy in a smaller atom. That's part of the reason we want to use a big one. Okay, it's not going to be able to sustain it. We break it, and there's just not enough of it there. Okay, and what else?
Isn't it because the more particles, the less forces holding it together, which means more radioactiveness, making it more stable?
Exactly. The smaller atoms tend to be more stable. The bigger atoms tend to be less stable because those small electromagnetic forces that hold it together are not going to work over larger radii or larger distances. Okay, and the other reason is simply target. Okay, you ever heard the expression, I couldn't put a bullet through the side of a barn? Okay, well, a uranium atom is like shooting at a barn. You're probably going to hit it even if you're a really bad shot. Okay, but put a P on top of a fence post and you're probably not going to hit that. Okay, that's the difference here. One atom's huge and it's an easy target, and when you hit it, it breaks into a whole bunch of pieces that go off and hit other things. If you're shooting at a tiny little atom, you're not going to hit it. And even if you do, you probably won't split it. It'll probably just move over. Okay, it'd be like playing pool. One ball hits another ball, it doesn't break it, it just moves it. Right? So that's why we wouldn't use the small atoms. Okay, number 10, atoms are indivisible. Okay, why was that statement believed for so long? Because we couldn't prove otherwise. Okay, we didn't know about things like radioactivity and nuclear fission and nuclear fusion. Okay, it wasn't until people like Marie Curie and Henri Becquerel and people like that discovered that some atoms are radioactive. Unfortunately, they had very short careers and lives. Okay? In fact, Henri Becquerel's desk is still on display in a museum, and it's still radioactive. Okay? Because they would like store their samples in their desk. Okay? They didn't know, right? I mean, you can't see radiation. You just got home from work and you didn't feel good. Right? Like these people were getting radiation poisoning because they were dealing with these radioactive elements and pieces of metal all the time. Okay? We just didn't know. Okay? And Yeah, you turn off the light and your desk is glowing. Oh, well, that's weird. No, not really. It doesn't do that. They just didn't know these things, and so they got radiation poisoning and died very young of cancer and things like that. So, yeah, we didn't know about those things, but now we do. We know that atoms do spontaneously, some of them anyway, break down. Okay, those ones are radioactive. Their atoms spontaneously break at a very slow rate. Okay, nuclear fission is us accelerating that. Okay, but no matter what happens, whether it's accelerated or happening on its own, every time an atom loses a particle, energy is released. Okay, that energy is in the form of radiation. That could be X-rays, gamma rays, okay, heat, light. Okay, all of those things are all forms of energy that can be released as an atom breaks down. All right. Number 11, from what you know of the structure of the atom, how do you think the atom stays intact? Why do electrons not fly off or protons separate from the nucleus? Because opposites attract. Very simply, there's electromagnetic forces of attraction that keep the electrons in orbit, okay, around the nucleus. Yes, they can move further away if they gain energy, but they still stay there. Okay? They will leave in a chemical reaction sometimes. The electrons will leave and go to another element, okay? But for the most part, okay, it stays together because of these atomic forces of attraction that are going on. Okay? And there's a force of attraction between a proton and a neutron. A proton is purely positive. A neutron is neutral. By comparison, it's almost negative compared to the most positive thing there can be. So there's actually attraction between the protons and neutrons as well. All right, and then number 12, the same principle that makes glow-in-the-dark materials work is used by plants to produce food. This was those electrons jumping or making quantum leaps from one orbital to another. Okay, and then when they return, they release that energy. Okay, in glow-in-the-dark materials, that energy is released as light. In photosynthesis, it's released as a form of like chemical energy that can be harnessed to break apart water and carbon dioxide to form glucose and oxygen. Okay, that's the process that powers photosynthesis. All right, questions on any of those? Okay, then we're going to move on to naming compounds here. So if you can take out your notes package to lesson 2, okay, that's what we're going to be on here next.